This is the recording for lecture 8, which happens to fall in the e-learning week. So there's not going to be a live lecture. So I have combined the usual supplement, which is recorded offline, and the live lecture into one. So this is going to be a bit long, but maybe I can suggest a few breaks along the way. So today's lecture is going to be about modularity and object-oriented programming, and we're also going to touch the topic of exceptions. We're going to go through a small tutorial on C#. So let us start. When we talk about modularity, we have to take into consideration the idea of stepwise refinement. Modularity is a concept that has to do with the robustness of code. We want code that is developed to be cheap to maintain, right? To be maintained at low cost and bug-free as much as possible, and as generic as possible so that it can be reused easily. And all these concepts appeared, of course, gradually as software systems started to become larger and larger. But by the 1970s already, the problem was quite serious, right? So many companies were writing software that had hundreds of thousands of lines of code. So people were researching the topic of making programs more modular and more generic. Niklaus Wirth, who was a Swiss computer scientist, right, and the inventor of the language Pascal, proposed that programs should be gradually developed in a sequence of refinement steps, so that in each step instructions would be decomposed in more detailed instructions. So that deals with creating levels of abstraction, right? Everything is a component. The components have their own subcomponents and so on, but you have to narrow down and focus one step at a time. All right. So Dijkstra came with his own type of examples and with his own methods. And he was essentially the inventor of structured programming. He was the one who relegated GoTo from programming languages, who proposed that GoTo should not be in programming languages anymore. So this is one example for printing the first a number of primes, right? So we start with a program that looks like this, and of course this instruction is too strong and cannot be implemented in any of the existing programming languages. So then we go on and start decomposing every component into smaller ones, right? So here already we have three essential components, and this is a declaration. This is a single instruction, and it turns out that this one would be more difficult to implement, so it has to be further decomposed, right? So here, as we go, right, we keep decomposing. Actually, at the time of Dijkstra, this one was not just a simple instruction, so it had to be refined in a very specific way. And this one, right, you wouldn't be able to print a full table as it is possible now. In Java, you just ask for a table to be printed and it will, right? So things had to be further refined. And step by step until every instruction that you have in your algorithm is implementable as a instruction in the language of choice, and then you have an implementation. So this leads to a program structure that is completely hierarchic. There's a main program. This main program has a number of subprograms, and some of the subprograms have further subprograms and so on. And there's a very strict hierarchy of dependencies. But it turns out, like later people noticed, that, you know, for instance, one subprogram like this one could be a component of two different higher level subprograms. So then we could have reuse at this level. And the question was then, how can we have as much reuse as possible, of course, because we don't want to replicate a programming effort. We want to avoid that. All right, so one important aspect is that as we perform this refinement, right, then these components could be further developed and refined in parallel. So they could be given to different programmers, to different developers to work on, right? So it's a great advantage because we can take advantage of some parallelism. If 10 people dig a ditch in, if one person digs a ditch in 10 days, then 10 people would do it in 1 day, right? Presumably. Not always true, but presumably. Okay, so we want to take advantage of a certain level of parallelism. And in this process, we don't just want to create a hierarchy. We want to factorize code as well. We want to create components in such a way that there's as much reuse as possible. So a different kind of hierarchy, which leads later to object-oriented programming, is to recognize the fact that, for instance, in a program we have several kinds of transactions, right? And they can be specialized in this way, right? We have deposits, we have withdrawals, and we have print statements. All of them are bank transactions. So if we have 3 kinds of transactions, we could assume that there is some code that is common to all of them. So we want to factorize it. We want to put in here common code, factorize, right? And then whatever is specific, we put in the individual components. All right. And in some cases, we can't just cut and paste. We can't just see that, well, this code directly applies here, and then directly applies here, and then directly applies here. This code may need to be generic, and then it has to specialize to work on deposit, specialize to work on withdrawal, specialized to work for the print statement. Okay, and this is where modularity, general concepts for modularity come in, right? So we want to create components, and these would be, in general, meaningful program units. And they would be, sometimes we just want to split the program into functions or procedures, right? Sometimes we just want to create data structures. Right? Sometimes we want to create modules. So we have multiple procedures in data structures grouped into one file, and we have several such files, each of them built by a program. So then, when these programmers, these developers, start working on their programs separately, the question is, how do they keep their programs compatible with each other, right? So these programs have to interact, and then you set a certain number of rules, and as you develop the program, you might think that there's always a need to develop new rules, and there's a lot of people to talk to when you develop these rules so that the programs remain compatible with each other, right? If you have n components, each programmer will have to talk to every other, each of the other n-1 programmers to work on these rules and make everybody agree on the same set of rules, which may be very difficult, right? Communication overload is really one thing that makes software projects very hard to complete. So then what came in was the concept of interface. So people write meaningful components and decide from the very beginning on an interface, which is a set of behaviors, essentially a protocol that constrains the behavior of each module, right? So in this way, if each of these modules has an interface, everybody else knows what to expect from one's module. If I'm writing a module, I have agreed on an interface with everybody from the very beginning, and as I develop the model and implement the interface, everybody knows what to expect from me. Nothing is no part of the interface is left to be created during the development. Right? So since the interface is now fixed, I can work on my module without interruption from the other guys because everybody else knows what they should expect from me. Just as long as I implement interface, everybody else is going to be happy. Right? So what do we define an interface? For those of you who know Java, right? In principle, in an interface, we just specify a number of functions. But if you think very carefully, those functions represent behaviors. Right? It's essentially how the object behaves. You call a function, the object does something, changes its state in a certain way, right? So it behaves in a certain way. So we want to express the behaviors represented as types and operations that are visible outside a component. So I have a lot of freedom in my implementation as long as I respect the interface. I allow the rest of the world to see what has been agreed upon from the very beginning. In general, what we want to be visible from our module has to be small compared to what we actually have to implement. And the car abstraction, the car example comes again into play because we have talked about how important the development of a car was in order to make it available to as many people as possible. The car is, in principle, right, a very complicated piece of machinery, right? But when it comes to driving it, right, it's actually very simple. The driver who sits here, right, has a number of pedals and a steering wheel and a few more controls that are not necessarily very essential. And the operation of these controls is very simple, right? So you can think of these controls, the pedals and the steering wheel, as the interface of the car. And all the systems that are present in the car, namely the engine, right, and the brakes. So there's an engine here, there are brakes around every wheel, which are essentials. There's a steering mechanism, right? All these are hidden from the user. The amount of information that is visible from the car is much less than the amount of information required to implement the car. And this is what we want in general from the interface. A good interface will not be overly verbose. It will be rather small and very clear, very concise, right? While possibly requiring a very sophisticated implementation. Now, in order to proceed further with the implementation, in general, people start with a specification, right? So instead of just sitting down and starting to code, we sit down and plan a little bit, right? We do a little bit of planning, and the result of that planning phase is a specification, right? Which refines a bit further what is the intended behavior of the component, right, and how that is observable through the interface. And only after that we can sit down and write code. And usually we start with the data structures, and then if the data structures are well designed, there's this expression that the code almost writes itself. So let's look at a case when the component that we want to write is just a function, right? A function to compute the square root. So the header of the function, the prototype of the function, if you think in terms of C, is the interface. And that's what we're going to agree on. Maybe we're part of a team of programmers, and everybody agrees that the function that I or you are going to implement is going to have this prototype. What you do inside is your business, as long as you allow it to be called in this way. You take as an argument a float, and you return a float. All right. So, in terms of specification, right? Because you see, this doesn't say a lot. What is the exact behavior? Well, we have to be a bit more refined. We're going to say that if x is greater than 1, then the product, right, the square of the square root is approximately equal to x. And you know very well that in general, the square root cannot be computed exactly. We only get an approximation. So if we invert that, all we get is an approximation of x. We won't be able to get the full thing. And then, once this has been finished, we can go on and have an implementation, right? And this is, I think, well, some method. You can figure it out how it works. Another example is a data type, right? And let's assume that the data type is a priority queue. It's a data structure that returns elements in order of decreasing priority. You may remember that such a data type is typically implemented as a heap, right? And what do we want to have? Well, we want to have a type. For the interface, we want to have a type, and let's call that type PQ, priority queue. If we're in Java, we're going to define a class called PQ. If we're in Haskell, we're going to define some algebraic data type called PQ, right? Anyway, PQ is going to be a user type, and it's going to be in such a way that it will ensure all the functionality of a priority queue. And then what kind of behavior do we have? What kind of functions? Well, we need to have insert, and we need to have removal of the maximum priority element, right? And these would be the types. Insert should take an element and a priority queue, and if we are in the context of a functional program, the return value would be different from the argument. We return a new queue with the element removed. Remember that in declarative languages, we cannot assign to a variable. If we are in Haskell, we can't change the value of a variable. So we take an argument and we return a new queue, right, where the new element has been inserted. Sorry, not removed. I think I said removed. Delete max will take a priority queue and will return a pair, right? The first component of the pair is the element which used to be to have the maximum priority in the argument, and the second component of the pair is the element, the queue where that element has been removed. So for specification, we have to have some sort of invariance. So insert will have to increase the set of stored elements, right? And delete maximum has to return the maximum priority element and the priority queue of remaining elements. So this would be our specification. Obviously, the size of these two elements has to be different by 1. So if this has a length L, this must have length L plus 1, or size, right? And if this one has size L plus 1, this one must have size L, right? We also want a predicate that allows an emptiness test. If the priority queue is empty, this should return true. And actually, we should be more specific here and say bool, not PQ, simple. All right, and then we go on to implementation, and you will remember your implementation from your algorithms and data structure module. I'm not going to insist too much here. Now, you see, in the specification of this data type, we were actually quite generic. We didn't say that this should be an integer, right? or a double or a string, we say that it's a generic element. It's a generic type. So this allows us to have abstract data types. Whenever we leave things unspecified, whenever we hide away details, we perform an abstraction step. And this is very good because it makes the code more generic. It's usually easier to reason about. All right, and also it naturally enforces modularity barriers. So we kind of know from the abstract data types what kind of modules do we need to implement. Most often we implement modules that implement certain data types, right? So we decide that we're going to have a priority queue, then we have a module that implements all the details of the priority queue. All right, now there's more to it. In fact, with abstract data types, we can separate interface from implementation. And this is an important concept, right, which has been illustrated when we talked about the car abstraction, right? There's a lot less information in learning how to drive a car than in learning how to build a car, right? And we want to keep them separate. We don't want to force the user to learn the implementation details. This has a number of advantages, right? Most obvious one is that more users can take advantage of that module, can use that module. If they don't have to know what's inside, right, they will just learn the interface very quickly and be able to use it. But the other thing is, the other advantage is that the implementer has the freedom of completely changing the implementation without having to let the user know. And this is also something that has happened with cars, right? Is driving a diesel car different from driving a combustion engine car? No, right? So the fact that you have an engine doesn't really matter what kind of engine, right? But the engine is a major part of the implementation, and the manufacturer is free to change the implementation, to change the engine, and give you a car which requires the same knowledge so as to be driven. And that will have fundamental effects on, for instance, fuel efficiency, right? And in the case of computer science, for instance, you can have the following scenario. You need to implement a collection, and you realize that you have to do it very fast. You have to do it very quickly. And then you implement a collection as a linked list, because this for you seems the easiest way to do it. And then that list, whenever you have to perform searches in the list, right, it's linear, it has low performance, but it works. The functionality is all there, right? You have a function that allows you to add to the collection, a function that allows you to remove, a function that allows you to check for membership, a function that allows you to check for emptiness. And then later, in version 2.0, you come up and change the implementation into something more efficient, maybe a sorted array or a binary search tree, or something that requires more effort to implement. Nevertheless, from the outside world, from the viewpoint of the user, there is no change. Everything is used in the same way. The user's program, the user's code doesn't need to change in any way. Nevertheless, the user will notice improved performance. We'll see that all the operations that he performs against your module are actually much faster. Another important aspect of data types is that in order to be very thorough about the specification of data types, you are forced to use type checking, and type checking enforces separation. All right, so there are a lot of important advantages in abstracting and creating abstract data types. Abstraction leads to generic code, and generic code leads to reuse, which leads to lower development costs. All right, so modules actually go in the same direction. Is a jump construct for information hiding. A lot of the things that we said about abstract data types is valid about the modules, all the more that usually you would implement the behavior of an X-ray attack through a module, right? So you want the module to have an interface, and you want the module to have an implementation, and you want a separation of concerns here, right? The interface and the implementation should be as separate as possible. Historically, they appeared in Modular. So this was the first language that allowed a program to be built from separate files. And then now we cannot imagine a modern language without modules. Every single language that is in widespread use has modules, has the ability of building programs from separate files. Obviously, there's a link, right? Generic code has to be implemented in modules. We want the modules to form a library. We want to write modules that can be made part of multiple applications, right? And this is definitely the case because you look at a variety of such modules. For instance, the java.util.star is a collection of modules that can be that contains implementation of basic data structures that can be used in a large variety of modules. It's a library, right? So the code that is written there has to be as generic as possible, has to be as abstract as possible. All right, so again, I touched a little bit on this. We want abstractions to be as generic as possible. We want a level of parameterization. We want to invoke a module with parameters and specialize it for a specific function. So, for instance, in C++ has templates, right? This was actually the first very important mechanism for generic code, real generic code, right? Then we have ML functors, right? And actually these are related to category theory, but they appeared around the same time. If you want to look for examples, this is the standard template library that comes with any C++ implementation. It's available in source form, so you can just go and open the files and check how they can be, generic abstractions can be implemented. All right, so let's talk a bit about C++ templates. They are relevant because nowadays we have Java generics, and we also have C# templates. So it's a form of polymorphic typing, and it's become very popular. These templates are similar actually to the macros in C, right? So in a way, what they do is they generate new code at compile time. They are evaluated at compile time. Nevertheless, they are type checked, which is not true about macros, right? So with macros, because of the lack of type checking, it's possible to get an error, a compile time error, and not really be able to trace it to the source. Whereas in C++, when we use templates, it is in general possible to trace the type error to its actual source inside the template that introduced the error. So C++ has class templates and function templates, and so has Java nowadays and C#. They're essentially the link time, right? And that will lead to a separate copy of template generated for each time. So we don't talk much about link time anymore because nowadays most languages have dynamic linking. However, C++ is an old-fashioned language, right? It built on C, And for C, when we built an executable, we actually have two separate compile and link phases, right? So we can talk about things that happen at actual compile time. The compile results in a .o file, and an object file, where the link results in an executable file. So we can talk about these two different things. However, because most languages have dynamic linking nowadays, there would be a certain level of linking that has to be done by the compiler, but it's no longer done by invoking a separate linker, right? For C++, the linker is a separate executable, a separate command that is invoked in the background by the GCC binary. But for Java, for instance, whatever limited amount of linking needs to be done there will be done by Java C itself without the invocation of a separate compiler. Now you're going to wonder why code duplication, why having separate copy of templates for each time, right? So if I have a class C, and if I say int C int, and then later I say, and I declare some variables, and then later I say C double, and then I declare some other variables, right? This template for the class C, right? I would have one copy that where T is where the parametric type is instantiated with int, and another one where the parameter is instantiated with double. So you may wonder why the code duplication, right? Why not just reuse the code? But it has to do with the fact that a lot of things vary dependent on the type, right? So double, remember, is a 64-bit piece of data, int is a 32-bit piece of data, and then activation of records will have to be resized. Allocation sizes will have to be changed, and so on. And of course, we can find solutions where we would have a single copy of the code, but that in general would be less efficient because it will have to perform tests. What's the size of my data, right? What are the possible operations for my type? Do I employ addition for integers or addition for doubles, and so on? Whereas if we generate two separate copies, then these tests are not necessary anymore. In general, these days, memory is cheap, so we don't care that much about duplicating code at compile time. We don't want, however, to duplicate code at when we write our function. So the human should not duplicate code, because then whenever you decide to make a change later, right, you will have to make the change in multiple places, and obviously that's going to require more effort. So for the human, you always want to factorize code. If the code is produced automatically, for instance by a compiler, then we don't mind that much, right? Typically, code duplication would lead to improved performance. So let's look at two examples, a monomorphic one and a polymorphic one. The monomorphic swap will only swap integers. The polymorphic swap will swap any time, right? And notice the fact that the code has a pattern, right? If I parameterize the int in the first version, I obtain the second version. So that's what we want to do. We want to extract patterns of computation and make them generic, right? Polymorphism is a format of generic code. Okay, and then in general, for instance, if we have such a class, right? Whenever we perform a swap, the correct version will be chosen by dispatching on time, right? So there will be one version of this function generated for integers, another one for floats, and whenever we call this, the compiler looks at the types of these two arguments and picks the correct version. As I said, a very good example of generic functions is in the standard template library, which can be studied. It's very easily accessible. It's one of the best examples of generic programming. It has inspired subsequent generic code libraries in other languages, most notably Java. You should know that also, right? If there's this myth about C++ being a relatively slow language as compared to C. This is no longer true. There have been very aggressive advances in compiler technology lately, and most languages, so C is in general the fastest language. That's still a given because it's very close to the machine, very close to the assembly language. But 10 years ago, we had a situation where C++ would be in general 10 times as slow as compared to C, and Java would be 50 times as slow as compared to C, and many other languages like ML and Haskell would still be between 20 and 50 times slower. Nowadays, if you look at benchmarks, all these languages are not worse than 3 times as slow, right? With many languages having very close performance. So C++ is in general less than twice as slow. It's about 1.6 times as slow. Java is about the same. Haskell and OCaml are in the range of 2.3, 2.4 times slower than C. So with the recent advances, most languages have become very fast. What do we have in STL? Well, I'm hoping that those of you who have studied Java would know about containers and iterators and collections, right? So all these are available in STL as well. And let's go through a very small example. Right, so a function to merge two sorted lists, they would need what? Would need ranges, right, of S and T, which are the sorted list. There would be a comparison method, right, which takes two elements and returns either -1 or 0 or 1, depending on whether the two first arguments are smaller, right? The first is smaller than each other, or it's equal, or they are equal, or the first is greater than each other. And we return another list or array that contains the merged elements. All right. So we would always have like iterators representing ranges. Comparisons would be essentially we want a method, but we wrap that around with a class, and the polymorphism comes from the use of templates. So here we have a call to merge, where merge is a predefined function. It should be noted that most languages have such facilities, right? They would be, and even for C++, there are many other ways of performing the same thing. So in C, we would use the function quicksort, right, as shown there. Compareint would be a pointer to a function with the same functionality, right? Returns -1 or 0 or 1, depending on how its arguments are smaller than, equal, or greater than. C++ in C++ we can also do the same thing on using raw C arrays. You remember that C is mostly a sub-language of C++ nowadays, right? So you can write a C program but compile it as a C++ program. You can also do the same thing, sorting an array with the vector class that appears in STL. In general, STL is quite efficient. um, right, is um, strangely more efficient than the quicksort in C. And the even stranger thing is that the vector class version is faster than the raw arrays version. People are wondering, so it's not, it's not completely well understood why this is happening. And that actually might have changed. So that was a few versions of GCC ago, right? These numbers. The important things are so far that generic abstractions are definitely convenient, but can also be efficient, right? So there's this myth that if you use abstract code, then you're going to lose efficiency. With recent advances, that's no longer true. But when it comes to C++, indeed, the code size may be very bloated, but that's not a problem today anymore because memory is huge. So we already have the elements of object-oriented programming, right? So I'm going to go through the aspects that we sort of discussed without actually saying what they were. So we have talked about encapsulation essentially, right? We have talked about the fact that information needs to be hidden. We only expose the interface and we hide the implementation, right? So this boils down to the concept of encapsulation, which is enforced in object-oriented programming. Right? We generally discuss it as something good to have, but object-oriented programming is where it is enforced. And let me try to help you understand the difference, right? So, of course, we want, you would think that in a collaborative environment, people just go by the rules, right? Comply with the rules. So if I'm saying that, well, this is the interface and you don't touch my implementation, it means that you don't touch my implementation. Of course, you're free to look inside my files, but you can't change it, and you shouldn't be accessing data, or you shouldn't be calling functions that are not part of the interface. Why is that? Because my assumption is that since they're not part of the interface, I am free to change them later as I please. Later, I may want a different kind of implementation, faster. I may want to write different helper functions. I may discard some of them that I have written, and so on. So if you don't, if any of the members in my project don't go by the rules and they sneak into my file and they find this function that is not exported, for instance, but it's useful to them, and they say, oh, let me call it because it helps me. Right? What's going to happen later is that when I decide to remove that function, right, the other guy's code is going to break. It's not going to compile anymore, right? And that will cause extra costs in development, delays, and so on. So now, with enforced encapsulation and object-oriented programming, I can declare fields in my, so the notion of the class, of the module, right? So we have objects, right? And they come from classes. The template for an object is the class, right? And actually the class serves as a module. What modules are in other languages is represented by classes in object-oriented programming, right? So for elements of a class, some of them I can declare as private. Right? Private means not accessible from the outside world, right? It doesn't mean that I'm protecting. I want to keep secrets from my teammates. They are always free to look into my file and see how I implemented things, right? But I don't want, in spite of they having that information, I don't want to allow them to call a function that I don't want to allow them to call. I don't want them to access a piece of data that they're not supposed to access. Simply because I might change my mind later and change the behavior of that data, right? Whatever is part of the interface is public and is cast in stone, and I'm not going to change. Everything else is game. Okay. We also talked about the notion of subtyping, right, which comes from polymorphism. Right? So subtyping is about building, for instance, a priority queue, right, where the element type is ELT. So then later we come and say that ELT should be int. So then PQ int, right, is a subtype of PQ ELT. Right? So polymorphism ensures generic code, and in the context of object-oriented programming, this is actually called subtyping. Subtyping and polymorphism are very much the same thing. But we have two new concepts. One is that of inheritance, which allows code reuse. We want to be able to reuse code. Remember that, because that leads to smaller development costs. And then we have, in order to allow inheritance, we need this notion of dynamic lookup. We need dynamic linking. Linking has to happen at runtime, and whenever I call a function calls another function, right? Or as they are called in object-oriented programming, methods. So we have methods, right? So as a method calls another method, where that method resides has to be decided at runtime, right? We dynamically look when method f, right? F is a method. And inside here I have a call to G, right? So the place where I can find G is found by dynamic lookup. At runtime, right, when we get to the execution of this, that's when we look for G. And you will see that it's not always the case that this G can be determined as at compile time, right? This G is completely dynamic. Okay, so these four characteristics are absolutely essential for object orientation. All right, we want the dynamic lookup is an implementation technique, but we want, as essential concept, we want encapsulation, we want inheritance, we want subtype. The program will be organized in a variety of ways. A very important and pervasive concept nowadays is that of design patterns. Design patterns will give you hints on how to organize a solution to a problem, right? And then from that, how can you organize your software and the software development process. All right, so another interesting issue is how does the power of object-oriented programming compare with the power of other concepts in programming languages. For instance, we would like to figure out that objects are essentially equivalent to closures. We can implement closures with objects, and we can implement closures with objects with closures, right? So there is an equivalence between object-oriented programming and functional programming. All right, so what's an object? An object essentially is made up of hidden data and public operations. Public operations are defined by the interface, and the hidden data is part of the implementation and is up to the implementer. Right? Nobody else outside of the, apart from the implementer, has to worry about the data inside. The operations act as policies. So, for instance, if an object represents a bank account, we would use a piece of data called amount, maybe as a float, and that will store the current amount in the account. And then this amount, should not go below 0. You can only withdraw everything you have, but you shouldn't be allowed to withdraw more. Well, some accounts have overdraft, right? So you can owe to the bank a certain amount, right? So you can have a negative balance, but even on that there's a limit, right? So there's a lower bound under which the amount cannot go. So then we cannot expose the variable holding the amount to the outer world, because if that happens, anybody would come in and assign to that value anything, to that variable any value they want, including minus infinity, right? Which would be completely um, completely inconsistent. Also, you might actually add arbitrary amounts to one's account, right? Which amounts to theft. So what you want is not just that your amount should not go below a certain value, but also to enforce that every increase in the amount is the result of a transaction that transfers money from some other source. There's no money do not materialize out of the group. So then the operations that access the data, right, it would be public, but they would enforce a policy. We would have a method set of balance, for instance, but to a certain amount, which is given as an argument to this method, right? But this amount would be checked to be always positive, for instance. So let's say we have a private amount, and then we have a public void set of float x, for instance, and we would say here amount is assigned x, right? But we cannot allow any amount, so we'd say if x greater than 0, right, then we'll do this, else throw exception, right? Exception, blah, blah, blah. So because we can perform this test here, we're actually enforcing a certain policy, right? So having public methods that are allowed to access private data will enforce data consistency. And this is part of the concept called encapsulation, right? So encapsulation is about hiding the data so that various policies of data usage can be enforced. Now, how do objects interact with each other? Well, they send each other messages. That was the view when this model was created. But in modern object-oriented languages, messages are in fact method names, right? So I have an object and I call the method with some arguments. In object-oriented terminology, we're saying that this is the message that is sent to the object. And in the first object-oriented language called Smalltalk, this actually was indeed the case. We would have an object which would receive a message as a message tag and a number of arguments, a1 up to ak, right? So this is how it was represented. And when we would build a message, an object, we would not build it out of methods. We would build it out of reactors, right, which were pieces of code deciding what would be the behavior of the object in response to a certain message coming in. So since C++, however, which was the first successful object-oriented language, because of its relationship with C, methods that do not have this kind of syntax that would actually appear as a message, but they have more of the syntax of a procedure call the same way as in C. So the object becomes a universal encapsulation construct. It can hide inside any kind of data structure, right? It can implement abstract data structures. And they can become anything. They can become a file system. They can become a database. They can become a window in a windowing system. And they can be an integer, but not the base integer, not the 32-bit integer, but an integer, for instance, that has infinite precision, that can also model plus and minus infinity, and so The metaphor is a bit ambiguous, but in a way that is useful. It doesn't really say whether the computation should be sequential or concurrent. Actually, many people think that since we're talking about these objects that live inside the program and interact with each other, there will be implicit concurrency. That's actually not true, and you know that from Java. There can be concurrency, but in Java the concurrency is not implicit. Nevertheless, it's not difficult to go from a sequential setting to a concurrent one. Whenever we talk about concurrent or distributed computation, all of these require computation performed in parallel. We would have synchronous or asynchronous communication between them, right? This is also quite easy to implement. You can always think of the method calls as messages. In fact, Erlang, which is a language that is specifically created for concurrent execution, has an object-oriented model, and actually there you can think of method calls as messages, right? Messages between concurrent entities, and you can think of processes as the same as objects, right? So there's a parallel between processes in our Erlang and objects in object-oriented language. So then you would have implicit concurrency in an object-oriented language. Now, object orientation counts as a programming methodology. So it has a number of concepts that are useful in designing software, and they're very useful at building extensible systems, right? So if you have the experience of Java, you have seen how many libraries and APIs there are. All these, many of them are third-party, are not part of the package that is delivered by Sun Microsystems. So they are essentially extensions to the original software development kit. These are the important concepts that are specific to object-oriented programming. You should remember them, right? And there are many languages that may not be fully object-oriented, but they are enabled as far as object orientation is concerned. So in this category, we have most of the languages that we have discussed so far. Haskell is not, but OCaml, Python, Scheme, obviously C++, Java, all of them have objects, all right? So you should look for how these properties can be realized in arbitrary languages. And we're going to see, for instance, later today, how C can simulate object orientation, right? So even though it has no concept of objects whatsoever, this concept can be easily brought in through a clever systematic translation scheme. All right, so let's explore the concept of dynamic lookup. Let us understand, what do we mean by dynamically looking up the method? Dynamically looking up the method that needs to be called in a certain context. Right? So what we need to understand that in object-oriented programming, as we use inheritance, essentially the meaning of an operation changes, right? So this is one fundamental difference from abstract data types. So we can essentially replace a method by another. That's what it boils down to, and we never know in advance which method will be called. Which of the many methods with the same name that appear in a family of classes that are sort of, one is the subclass of the other, which of them will be called, right? That is decided only at runtime. So let's look at an example of adding two numbers, and we can represent this number in this way. We are assuming that x is the object, and it received the message add. We're just going to use this syntax that is, well, it's not really, actually it sort of is, because you can assume that in C++, you can assume that this is a pointer to an object, and then we need to have an arrow, and this would be a method inside x, and it takes as an argument y, and maybe it performs the addition of x and y. Since inside x we can replace the add method, right? We do not know in advance which add will be called when we evaluate this expression. In conventional programming, we would perform this kind of operation, and add is a procedure that has been defined as part of the code and has a fixed meaning. Its meaning cannot change throughout the run of the program. With dynamic lookup, we can very easily implement polymorphism, right? We know very well that, for instance, integer addition is different from real addition, but most of the times this is possible because, and we're using the same operator for both, right? And this is possible because plus is a predefined operator and is treated in a special way by the compiler. However, in an object-oriented language, it's often possible to define our own operators, many of them with the same name, right? We can even redefine existing operators and make them have different meaning depending on the types to which they apply. So, for instance, in C++, we could define a new type called complex for complex numbers, and we could make plus an infix operator between complex numbers as well, with the standard implementation for complex number addition. So this is part of the dynamic lookup scheme. All right, so the other concepts are encapsulation, subtyping. In inheritance, we want to keep talking about them. We actually covered encapsulation quite a bit. So it emphasizes the fact that the user has an abstract view of the data and has no direct access to data. It only has access to it through certain methods that enforce a given policy, and in this way we have a separation of concerns, right? Encapsulation separates two views. One is what is the implementation, which operates on the representation and enforces the policies, and the other side is the usage, the client code, which operates on the abstraction, just takes advantage of the operations as if they were fixed. The client doesn't need to be concerned on how the operations change. All right. So the client may write his or her code on the numbers. Right. Let's say you want to compute the power operator between two numbers, a to the power of b, and you write your code for numbers, and the code should work irrespective of whether the numbers are integers or reals or complex numbers, right? And the user might not even be aware that later a complex number is going to be created. If he writes the program in terms of the abstract view that is offered by the interface, his program will still work on the complex numbers that were not available at the time when he wrote his code. Right, so this is a really powerful and very useful approach. Okay, so subtyping and inheritance. Subtyping is a realization of polymorphism, and inheritance pertains to code reuse. In general, the view for inheritance is the following. We can we can have an existing class with many methods. So we have method 1, method 2, method 3, method 4. And then we define a subclass, right? We define a subclass, right? And the subclass inherits most of the methods, but it replaces one of the methods. So this one is no longer available, right? Now, the interesting thing is the following, right? So these are the methods, actually is the same code as here. So in the previous code, what used to happen was that this guy might call this guy, which might call this guy, then it returns here, right? But now this one, which is in the middle in the string of nested calls, in the sequence of nested calls, this one doesn't exist anymore. It has been replaced by this guy. Well, because which function we need to call is decided at runtime, all right? This guy will not be statically linked to this guy. It will first say, well, where is my method m, right? And now, as a result of dynamic lookup, it will discover that m is actually here. So it will perform, do I have a different color that's used, the green? It will perform this call. This guy can now perform this call. This guy returns, and then this guy returns, right? And this method has pervasively replaced this method, which does not exist anymore, right? So this ability facilitates code reuse to a great extent. We can take a set of procedures that are inside a class and replace any of them at will, and the replacement is pervasive, right? So you can think of what do you mean by reuse, right? All the other ones are reused in a very useful way. They're reused because this guy, right, I'm reusing this guy, I'm not writing a new one, and this guy is capable of calling the new procedure instead of the old one, even though it wasn't aware that the new procedure would ever exist at the time when it was written, right? So that's very important. So with inheritance, we have code reuse. That reduces greatly software development and maintenance costs. All right, and again, here we should remember the object interfaces, right? Once after we have talked about what objects are. So objects are essentially modules, and we have seen that modules have interfaces. Therefore, we should talk about object interfaces. And you should be very familiar with this because of Java. Those of you who have studied that, right? You know about Java interfaces. So the interfaces will be an abstract perspective on the object. It will sort of say something about the behavior of the object without saying anything about the implementation. Would only allow visibility of methods instead of visibility of data. And you can regard the interface of an object as a type. So this is very important, right? You can regard object-oriented languages as typed languages. If we are in the presence of, in an object-oriented language, actually we have two types of subtyping. Very important. One comes from polymorphism. So a list of generic elements, right, is a supertype of a list of integers. And that can be achieved, and that is actually specifiable in all object-oriented languages via templates. But also, we can have a class being extended by another class, by a superclass. So, in that case, the subclass becomes a subtype, right? What's the advantage of a subtype? Why is it important to be aware of subtypes? Well, if I have defined a procedure that takes point x as an argument, well, guess what? If I create a variable colored point called y, because colored point is a subtype of point, I can come in and replace or actually use y as a parameter of f. Right? The simple fact that colored point is a subtype of point allows y to be a parameter of an argument of it. So that gives that makes reuse software use even more pervasive, right? Because now I can reuse old functions with new types, right? When I wrote function f, I wasn't aware that there will ever exist a color point will ever exist, but now that it does exist, and since it is a superclass of point, I can immediately take any data of type color point and use it with functions whose argument is point, right? I don't have to write new functions. All right, inheritance is just an implementation mechanism, right? It's the ability to create a new class where I replace a few methods from the old class, but I reuse all the other ones, right? So I inherit all the other ones, right? That's why the word inheritance comes from. The subclass inherits most of its methods from the superclass. It just creates a few new ones, it replaces a few, but most of them are inherited. So, right, this is an example, the same example. How does inheritance work here? Well, essentially, right, if you look at the definition, all right, let's look at the definition. What happens really is that, right, if we are in an object-oriented language, we actually don't have to define this. So we don't define this. We don't define this either, right? We simply say that this extends point, and then these fields will be inherited here. Okay? So these behaviors will be inherited, right? So a colored point essentially becomes a kind of point because it extends point. It is a kind of point. Any object of type colored point can be passed as an argument to a function that accepts points, right? So we have subtype. All right. So in terms of program structure, right? So how do we go about organizing our programs? What we want to put together is the data and the functions that operate on that data. Actually, this is a general principle. We would do it in any language. We would do it in Haskell, which is not object-oriented at all, right? And this grouping is realized with a program unit, which is called a class, right? So the most basic kind of component in a object-oriented programming language would be the class, right? And objects are created as instances of that class. And the class groups together data and functions, and in this way, it essentially defines behavior. Defines the behavior of all the objects that are instances of the class. Then we have relationships between classes, right? So some classes are related to some other classes. So we want to create subtyping relationships within these classes, right? By having one class extend another. And once we have subtyping in realized in this form, we almost automatically have inheritance, right? And what we want to do is avoid re-implementing functions that are useful and already defined, right? I'm extending the class that has those methods, and I reuse those methods. I inherit those methods. A very typical example, there are many, right? So their object-oriented languages would be very good at defining libraries, very generic libraries. Right, so if we were to implement the geometry library, we would start maybe with a general concept called shape, and then shapes will have various subtypes of shape, which would be circles and triangles, and all the shapes need to have the following properties or behaviors, right? We need to be able to compute the center of the shape. We need to be able to move a shape from one place to another. We may need to rotate a shape. We want to print a shape, right? And all these properties and behaviors should be common to all shapes, irrespective of whether they are circles or rectangles or triangles or anything else, right? So you can see now how if we are able to write these four methods for the class shape, we can then later inherit them into the other subclasses like circle, rectangle, triangle, and so on, right? So these would be defined here, and then from here they would be inherited into circle and rectangle. In general, one great skill of software designers is to anticipate, be able to anticipate and organize the code in such a way that it can later be extended very cheaply, right? Anticipate additions. So now, every shape, every subclass of shape should come with an interface, and that interface should include those four methods, right? And then we can worry about the implementation. How would we implement a square? How would we implement a circle? Notice that shape would be a completely generic class, would be an abstract class, because we're is it too underspecified to simply have instances of shape. We either want to have squares or circles implemented in practice, instantiated in practice, but we want to refer to them as shape because often enough we want to put them in a common group. So once we define these classes and subclasses, we essentially create a subtype hierarchy, which can actually be very deep. If you look at the various APIs that are available in Java, for instance, most of the documentations will give you the type hierarchy, and you can see these trees that sometimes are very deep. And guess what? You, in using that library, have to extend the hierarchy further. You have to create new subclasses of the existing classes. The code is placed in classes, right? It's placed inside methods, and that makes it possible to have dynamic lookup, to look for the method at runtime, right? After the method maybe has been replaced. So now we can use them, and what we will assume in general is that we have a number of shapes placed in each of the shape would actually not be just a shape. It's either a square or a I think we have rectangles and circles and maybe triangles and whatever, right? But when we want to process the entire collection, we want to refer to them as shapes, and we want to take advantage of the common behaviors that they have. We don't want to be overly specific, because then we would have to implement a test and say, if this is a circle, then do this, if this is a rectangle, then do that, and so on. No, we want to refer to all of them as shapes, and we would have patterns of computation, right? Like a control loop that doesn't really need to care what specific kind of shape it is, and can process something like printing for each of the shapes in the collection. So, moreover, right, we were saying that we're putting our shapes in collection. Collections are actually abstract. We don't really deal with collections. Collection is an abstract class, and we have subclasses such as string and dictionary and set and sorted set. All right, and we refer to all of them as collections because they are capable of holding elements. That's what happens there. They are capable of holding elements. But in most cases, we just want to refer to it as a collection. We don't want to know the specific kind of collection that we have. So this leads to design patterns, right? When you think of, I have a collection, I want to do something for every element in the collection without really caring very much about whether the collection is a set or a list or an array or whatever, and whether the objects are circles or rectangles or triangles or whatever, right? So we have shapes inside a collection. Shapes are abstract, collections are abstract, and the processing of this kind of situation, which essentially is writing a loop that iterates through all the elements of the collection and performs a certain operation, this becomes a design pattern. This design becomes a program pattern, right? So people have identified a number of design patterns and have come up with code templates for implementation of these patterns. So you can just take a book, like for instance, there's one written by a guy called Gamma. You can take his book on design patterns, learn the patterns, and then look at a problem in practice and figure out which pattern applies, and just take it from the book and implement it directly, which makes implementations a lot more systematic. So this is what I was telling you about design patterns. Examples of design patterns are for instance, a singleton, right? A singleton is a program that has a class, and there's only one instance of that class. And that is useful, for instance, because you may want to keep inside that instance information that is global, that pertains to all the components in the program. For instance, right, you would use it for communication between threads, and it's a global data structure. You don't need multiple instances of that. There are many other uses. So singleton is one. We also have the visitor design pattern. The visitor design pattern, you can think of objects in general as being loosely connected in a graph. And I'm saying loosely connected because often enough you don't have arcs that tell you which node is connected to which. You sometimes access the sort of neighbors of an object by calling certain methods, and those methods are not always the same, and the number of neighbors is not always the same. Nevertheless, conceptually speaking, the notion of depth first and breadth first traversal apply, right? And this leads to the visitor pattern, where you traverse a network of objects performing a visit, a certain operation on each node, which is indicated as a generic operation. Visit, it can be anything specific, like counting how many objects there are, or whatever. You can figure out a variety of uses. So we're relying that all the objects in the this network of objects have two methods: the accept method and the visit method. And accept should call visit. So, for instance, if you look at a car has a number of elements, right? All the elements are objects, so you can think of the car, whenever you have an object of type car, as having four neighbors, which are or sorry, having several neighbors, which are the components of a car. So here we are assuming 6 neighbors, 4 wheels, and a body and an engine, right? So this is overly simplified, but it illustrates the concept nevertheless. So what we want here to happen is that um, uh, we want to go through each of the objects in the network, and notice that we don't have arcs. An object is accessible via a method will be accessible via a method or via a variable. So all we can do is follow all these links, look at all the variables, look at all the methods and see what they return, and make sure that for every object that shows up our way, we go there and um, visit the node. So notice how we take advantage of the visitor method, right, which is part of an accept method, right? So visitor becomes a parameter. We try to abstract and make the code as generic as possible, and this is as far as we can go, right? We don't want to be overly explicit. All right, so because of this, we want to make the code belong to the pattern, right? So an essential aspect is adding a new method to each component class. All the classes that are part of the car now will have their own visit method, right? So that method can be called by the accept method that is essentially implementing the proper. So, right, and we get to a point, right, where we would have this class do visitor, and this class simply visits every single part of the um, of the car in this case. All right, so this is pretty much what I have to say about general concepts of object orientation, and this in principle would have been the content of the live lecture, and this is a good place to take a break. However, and I will be taking a break right now, but I will continue inside the same recording. Right, I'm going to pause and continue inside the same recording. So maybe it's a good point. It's a good point for you to pause the play of your file and resume it a little bit later. Take a little break. So, in our second part of the lecture, we will try to offer a systematic translation scheme for object-oriented languages. I'm going to start with a Java program, right, that showcases the concept of inheritance, and then I will translate that into C. I will use a systematic translation scheme to have a C implementation, and hopefully that will showcase the basic principle of the how inheritance is implemented. So let's say we have several classes. The basic one, the most basic one, is a class called speaker, right? Where the speaker only has one method called say, and the speaker is capable of just saying, echoing whatever the argument is, right? So if we have an object of type speaker, and let's call it George, and we say George.say hello, then what is printed on the screen is hello. Now we have another class that extends the speaker. We call this one lecturer. Well, the lecturer says things and then reminds the class to take notes, right? Well, it doesn't really happen anymore, but let's assume that it's a more old-fashioned lecturer in a time when most of the delivery was done on the whiteboard and students would have to take notes, so a good lecturer would remind students to take notes. So this lecturer can lecture, um, right? And whenever the lecturer lectures, it inherits the method say and uses it to say the message, and then add to that, you should be taking notes. So notice that this method actually comes from here because the lecturer extends the speaker. So that's where the method say comes from. All right. Also, a lecturer can use the method say independently. It doesn't have to use it from inside lecture. So if we have a lecturer, let's say Razvan, right? We can say Razvan dot lecture, right? Hello, and then what is printed is hello. You should be taking notes, right? But Razvan can also say things. So Razvan essentially has two methods, one being inherited from the speaker. And then we have yet another class called arrogant lecturer, which overrides the method say. So essentially replaces, because of this extension, this method normally would be inherited. But we don't want to do that, so we define a new method called say, and this new method overrides the one that would otherwise be inherited from the speaker. So this is the method say, and this method relies on the super method say, right? So you see, even though there's this thing, this overriding of the method, right, we can still access the old one by fully qualifying it. All right, then what does the arrogant lecturer say? Well, it prepends, it is obvious that. So if we have an arrogant lecturer called Albert, right, called Albert, then Albert.say hello, right, would be, it is obvious that hello, right? And guess what? Arrogant lecturer extends the lecturer, so it also has a lecture. This one is also inherited. So we can have the arrogant lecturer lecture, right? Hello. And then what the result would be, right? We're saying that, right? The arrogant lecturer lecture, the sky is blue. What happens then? Well, the arrogant lecturer is going to say, it is obvious that the sky is blue, followed by, it is obvious that you should be taking notes, right? So it will lecture, and in lecturing will say stuff, right? And the question is now at this point, which method say will be called? That's a very interesting one, right? Which of the says, we have two of them. We have one here, we have one here. Which of them will be called? Well, you probably guessed correctly. This one will be called, right? This is the essence of inheritance. We have replaced the method say, and all the procedures across the entire class hierarchy will call the new say instead of the old say. This is very interesting because at the time when we wrote the lecture, we were not aware that the class arrogant lecturer would ever exist, right? But now that it does, it essentially replaces the say that came from the speaker, right? So the lecture method, whenever it invokes say, it will call this say. This is what we mean by dynamic lookup. Only at this point will the system wonder which method called say should it use, right? If the system would have asked this question at runtime, at compile time, right? At compile time, the only possible answer at that time would have been right from here to go here. No other choice, because at compile time, each class was compiled separately. We first had the speaker available, then we had the lecturer. Whenever we are inside the lecturer and look at say, there's only one method say here, right? So at compile time, the only choice would be to call the say inside the speaker. However, with the dynamic lookup, the compiler says, I'm not worried. There's a call here, but I'm not worried where I should go. I'm going to leave this for later, till runtime. At runtime, guess what? This new method comes into existence, and then when we want to call from inside lecture the method say, the runtime system will make this link automatically. Essentially, right, defining a new method called say, but inheriting the lecture. Okay, so, right, this is what we have here, remember, right? The sky is blue, right? Appears on the screen as it is obvious that the sky is blue, followed by it is obvious that you should be taking notes. So now we want to do the C equivalent. And how would we do this? Obviously, we can only implement the class as a structure. We don't have that much choice in C. So this choice is kind of obvious, right? It's the only one we have. So we're going to define this structure, which we would call speaker. And inside speaker, we like to have a method. But guess what? We can't have a method inside a structure. The only thing we can have, or the closest thing we can have, is a pointer to a function. So we're going to call this pointer say. This becomes a field of the structure. What are the arguments? Obviously, the message is a necessary argument, right? It appeared in the previous version, so it must appear here. However, there's one more argument that we need in order to allow dynamic lookup. That argument is a pointer to the object itself, which we're going to call self. So this is going to be a bit strange, because you're going to say, well, the object is there, I have the method, why do I need the redundancy? Okay, and let me show you what I mean by redundancy. Let's say I have a pointer to the speaker, and I want to invoke the method say. So this is a pointer, and I call say, and the first argument has to be P again. This is what we mean by this guy. And then I can say the sky is blue. Okay? So whenever we invoke a method, this is how we invoke it. Pointer to object. Right? So pointer to object, arrow, method name, same pointer to object. Why? Because from this guy, I can always perform dynamic lookup. If I don't have this guy, I won't be able to perform dynamic lookup. I can only perform static lookup. So, since we have this pointer here, but we haven't defined the method yet, let us proceed with defining the method. This would be the method, right? So, as promised, it must have a self, it must have a message, and it will print the message. And you're going to see here, well, we're not using the self after all. Why do we have it there? We'll have it from uniformity. All the other classes will have it there, and there's an assumption that always the first argument of every method is the object, or a reference to the object to which the method belongs. All right, this redundancy will enable dynamic lookup, and we're going to see that soon. In Java or C++, this is called this, not self. All right. However, in languages such as Python and Ruby, the first argument is called self, and it is passed in most languages. It is passed silently. There's no explicit mention of the self, right? We know that from Java. So it's possible to have a method like f of int a int b, right? But inside here you can say this, the value equals a, for instance, right? So this that you can see here is essentially an argument. It's passed in the first position to f. It's an argument that goes right here. Now, we need a constructor. So remember that we need, in object-oriented programming, everything is constructed by a constructor. If we do not provide one explicitly, a default constructor will be created by the system. What do we do here to realize that? Well, we have the constructor. Nevertheless, we want to split the constructor into two. One that performs allocation of memory, and another one that performs initialization of the data. And one very important aspect of initializing the data inside the structure is setting up the pointer to the function. Otherwise, there's nothing to call. So notice that this init is called here. So we have the allocation, we have the init, and then the pointer to the new object is returned. We proceed in a similar manner with the lecturer, all right? And now we're going to have to be self-conscious, and we know that we're inheriting, but C doesn't have implicit inheritance mechanism, so we have to do the inheritance explicitly. We have to come in with the method say. We have to put it there even though it is not declared inside the class lecturer that we have written in Java previously, right? So we have to write manually this say right here. And it has the same structure, and we have another method called lecture, so we define another pointer to a method right here, and we have the interesting property, the following very interesting property that is of paramount importance here. So the speaker only has one field, which is the say method. The lecturer has two fields, right? There's a say and there's a lecture. All right? So what happens, right, is that C is prefix consistent as far as structures are concerned, right? So the first structure, right, the speaker, is a prefix of the second structure, which is the lecturer. So because of that, the fields will always be placed in top-down order, right? So because of that, if I convert a pointer to a lecturer, right? So I take the address of the lecturer, of a lecturer, and I convert it into speaker star. Well, guess what? This entire thing can still take a say, right? So we're actually pointing to this box, right? And I can say dot say because the bracket now is a pointer. Actually, I think here I should say arrow. I should say arrow, right? Not dot. So the bracket now is a pointer to a speaker. So this is a speaker. This is a speaker, but we are pointing here. But the system now believes that this box is in fact a speaker. And when it says arrow say, it will select precisely the correct field, the one whose pointer to function is the same as this guy, because of the prefix consistency. Right? Whenever I'm writing the fields in the same order, they will appear stored inside the binary in the same order. Right? So I can rely on the fact that I can always write arrow say here, right? And in spite of referring to a data type that is more general, actually is more specific, not more general, right? But it has at least these fields. It will be it will get a value that is consistent and useful. So we have defined this method, and we want to actually we have declared this method, right? Not defined, and we want to define it right here, and we're going to follow the code. So look at the code on the previous slide. You're going to see two calls to say. So we're going to do the same thing. We're going to have self arrow say, right? Self arrow say. The message is here, And when we perform the call, notice that we are passing the self. So again, we're seeing self, arrow, say self. Right? Previously we saw p, arrow, say p, blah, blah, blah. So this is the pattern. And if you understand one thing from this lecture, understand that in order to have inheritance, you have to use this. What's the role of this? Well, now, right, as it was passed in here, right? If this comes from an arrogant lecturer, right, this will be the arrogant lecturer, and self-arrow say will not really be this guy, but will be the say of the arrogant lecturer. So these are very important. We continue with the initializers, with the constructor, and remember that we have a constructor that allocates memory, and if it succeeds, it calls the initialization procedure. All right, and notice one important thing, right? What does the initialization procedure do? It first calls the initialization procedure for the speaker. So this is in line, again, with what you know from Java. If you remember, whenever a constructor is called, the first thing that the constructor does is calling the constructor of the super. So this is what we're doing here. We're not really calling the constructor, but we're calling the initializer, because we already have enough memory to accommodate both the lecturer and the speaker. All right. So then finally we have the arrogant lecturer. So this guy, going by the same translation principles, has has three methods, right? And again, we have to write all three of them, even though the first two are in fact inherited. And then we're going to create this pointer, and what's going to happen here is the following. We want to replace this method, but we want to still keep around the old method, just in case we need to use it. And you have seen already in the Java implementation that we actually do have to use it. So we call super with something at some point. Since we're going to clobber this, but we still want to keep the method around, first we're going to make a copy. We're going to take the old method say, and we're going to put it here, and then replace the say field with a new method, the one that comes from here. Right? So if you look carefully at this code, this is exactly what's happening. We allocate memory, and then we deal with this. It is obvious that, right, which the class didn't seem to understand very well. But just look at it for a while and try to understand it. Try to ponder about it, mull over it, right, and get to understand it. In the initialization, what do we do? So now it's very interesting. We initialize the super, but remember that the super initializes its own super, because now we have a 3-level hierarchy, right? We have the speaker, right, and the lecturer is a subclass of the speaker, and the arrogant lecturer is a subclass of the lecturer, right? So all the constructors must be cascaded. And then we initialize the data, right? So we set the say to be this guy, but the old guy, we save it into a field that we have created for precisely that purpose. All right, so we have a make here, and the make allocates memory, performs the init, and returns the value. All right, so now we have achieved what we initially wanted, right? So if we have a program of the type, arrogant lecturer. So we're going to have struct a lecturer star p equals make a lecturer right, and then what we're going to do here is p star say p and some the sky is blue. Alright, so if we do this 10 times, so notice that p, right, we're going to see it is obvious that the sky is blue, it is obvious that you should be taking notes. Alright, so remember this pattern. P arrow, method name, and P again. Right? It is redundant, but essentially, whenever we look for a method, we're going to look here. This is the most recent addition, right? This is a new function. And how does the lecturer, whenever the lecturer says something, how does the lecturer invoke the say of the arrogant lecturer? Well, because this is an arrogant lecturer. So inside there, whenever we do P dash say, right, as it happens on the previous line, so we are saying self say here. This self is in fact an arrogant lecturer. This say comes from the arrogant lecturer. It doesn't come from the speaker, right? So let that be well understood. All right, so I'm sure that the code is a little puzzling. Look at it for a while and try to understand how this concept works, and understand that you can essentially translate any Java into a C program, right? Just in case you're not happy with the performance of that library. So, right, this is the code, and we're going to go through this systematic translation scheme in detail in the tutorial. We're going to do it yet again. So I would get some feeling that you really do indeed understand this topic. All right, so let's remember that each class is compiled into a separate structure nowadays. Data members remain the same. All right, and the methods are changed, right? Instead of having the methods, because you can't put code inside a structure, we would have pointers to function members. So in the end, every method gets to be compiled into a function with a mangle name, right? We can't have the same name all the time, because then we would have name clashes. So we have to invent new names all the time. But we can have the same field name inside a structure. So it's fine, because I can have a say inside the arrogant lecturer and another say inside the speaker. All right, and we always have to remember to call the methods through the corresponding pointer and put the first argument be the argument of the current object. Be the current object, a reference to the current object. So, all right, maybe you can take now a short break again. Maybe pause it for a while and then come back. And when you come back, we talk about exceptions. Exceptions are useful for error handling. I'm not sure how many of you have talked about exceptions before. They are available in both Java and C++. The exception system of Java is fairly advanced, so it's in line with all the modern developments. But you might not be familiarized with many other constructs. The main purpose of exceptions is error handling. So in general, you would expect that you don't get into errors very often, and because of that, you sort of lack the practice of identifying bugs and corrected programs. And you can actually tweak the frequency of uh, the um, the errors, right? And the try-erase mechanism is in general not very efficient. It's not the most efficient way of doing things, um, but um, they in general respect a very standard syntax, right? There's a try-catch block, and there's a potentially we have a finally clause. The exception is actually generated, right, issued by the command throw. And this throw sometimes is called the raise. And some languages are very specific about using the keyword raise instead of throw. One being Haskell, for instance. Also, I think Python. All right. So exceptions. Let's look at an example, and then again, let's find a systematic translation scheme. So we're going to assume that we have a little program there with a try block. Inside the try block, we have, as a result of some error checking, we have an exception being thrown, right? And then it turns out that this throw needs to be caught by the immediately following catch clauses, and each clause is expecting a specific type, right? ex_1 and ex_2, and deciding which of the two should receive the thrown value. That is done on type, right? So notice there that each of the catch instruction, each of the catch construct declares. So first of all, they're pretty generic, right? But we have type specifications there, and we can check whether the type of the expression being thrown, the exc expression, matches ex_1 or ex_2. Okay, so the exception is thrown. Let's say we are throwing an exception of type ex_1. So then we're going to go from the point of the throw, right? So from here, we will go in here, right? Provided that exe is of type ex_1. If it is of type ex_2, then this guy is delivered here. So the dispatch is explicitly on type, checking where should we stop to allow the expression, the exception to be found is on type, based on the right hand side, we have a example. All right, and it's sort of a vanilla example, and at a point when I collected it from the web, because I'm not that good at inventing examples, especially the wrong type. Right. What we need to do there is so this would be essentially, I think, C++. So what we want to do here is simulate the try-catch block. So we're going to do that by essentially means of a go-to statement. And this exe, of course, cannot be created on the fly, so we have to create it somewhere. We're going to assume that this E has been declared as a structure, simple structure where we would have um, this T, and this field T records the perceived time, right? And guess what? Even though we initialize E as an exception, it may be the case that in reality no exception is actually being thrown, so there's no need for a companion for the lady that lost her husband. And um, so in this example, right, we're mimicking the code on the left-hand side. What do? We need to initialize the exception, right? So this is what we do here. This is what we do here, right? We need to have a certain encoding for exception, and that's actually very simple. We will use E as a structure, and there is a field identifying the time, right, this type here. And we're going to start with a special value for this field that means this is no exception, and only when we realize that we need to be throwing an exception, we change the type to the one of the exception that needs to be thrown. So we're going to rely on a go-to statement to perform dispatch to the correct catch, and this will the correct place will be inside a switch, and the switch will be labeled by this catch clauses, so we can go there and execute that code. So inside the switch, we dispatch on the type of the exception, and we're going to have all the types, and for each type of the types, we can put the code. So essentially, what happens is that the code that we have here is transferred here, the code that we have here is transferred here, and the code that we have for finally is transferred here. So notice the fact that the finally block must be executed all the time, irrespective of whether the exception has been thrown or not. And in here we can reach either from here, so the exception has not been thrown, so from here, right, we can reach here, or we can come from here, right? So finally has to be executed not in both cases. So we have to see exactly what we do in each of the two cases. All right, so now we need to be more specific, right? So when we implement, we're going to distinguish between two types of exceptions. We're going to have unchecked exceptions and checked exceptions. This is the standard terminology of Java. Unchecked exceptions are the ones that can perform arbitrary jumps and without being declared. So that's an important type of freedom that we have. We don't have to declare the exception to be thrown for an unchecked exception throughout the entire path of or hierarchy of nested calls, nested procedure calls that we might have. Whereas we'll see later for checked exceptions, if you remember from Java, we have to say that a function throws, we have to put such a clause. Either we catch it or we have to declare it as being thrown by the function. So now we have to decide what do we replace every component of the try catch construct when we go from C++ into C. We're going to do something along the following lines. So the try statement, essentially at the try statement, we save the first state. So this is for unchecked exceptions, right? including the current stack configuration. We're going to see that there is a special procedure defined in the C library for that. And we need to keep a global variable whose type is a structure that records all the information that normally we would put in the exception, right? So that will be the exception being thrown. For the throw statement, we fill up the global variable with the exception details. We restore the state, right, to the place where we saved it, namely the try, right? At try we save. So when we throw, we restore that state so we can go back to the try. And then at the try will be sort of implemented as an if, so that we can, inside if, we can skip directly into the catch statement. So this would be quite simple. This will allow, we actually need to allow nesting of the exceptions. So when we save the state, actually the saved state has to be placed in a stack, cannot be placed in a say global variable. So now each try will push the current state on the exception stack. Each throw will restore the state at the top of the stack. If the restored try cannot handle the current exception, we rethrow. Remember that finally has to be executed every time. Either we have thrown exception or not, we have to execute that. We have to execute the finally. So let's look at a piece of C++ code this time that we would like to translate into C. Alright, so let's say we have a function and we have a try code inside, and then inside the try block we call another function G, and then we go to G. Inside G we call another function H, and inside H, as you look carefully, we can throw one of two exceptions. So everywhere we have dot dot, you imagine that we might have some if statements, something in such a way that in some situations we might be throwing E1, in some other situations we might be throwing E2, but depending on the global state of the program, right, either being A1 being thrown or E2 being thrown is possible during the execution of H, right? Definitely not both. We can't be throwing both. But it's not the case that we hit E1 and then the exception is thrown, and it's never possible to hit E2. The dot 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 may have if statements that may avoid the execution of throw E1, so that throw E2 may be later executed. And also, even the throw E2 might be avoided. We might end up with a normal execution of H. It's not necessarily the case that H throws an exception every single time. Now, notice that inside H we also have a try statement, so we're trying to make things a bit more complicated so that it's clearer what every exception and every try-catch block is doing. So one of the exceptions, one of E1 and E2, can be caught inside H, namely E2. We have a finally block then there, and we might be either returning a normal value, or because of the exception, we might be, let's say that exception E1 is thrown, we might be jumping right back to the catch E1 clause, right, which is right here. Sorry. Which is right here, right? So when this is thrown, control will go right here. But do not forget to execute the finally. So essentially when E2 is thrown, finally is executed first, and then execution jumps to the place where E1 is being caught. So how do we implement this in C? Well, there's an important component that we need to use. It's a pair of procedures defined in the standard C library. They're called set jump and long jump. So they have a slightly strange behavior. All right, and we can see that by means of an example, right? So let's learn how set jump and long jump work by means of an example, and only after that we're going to go and see the systematic translation scheme for exceptions. So set jump long works in the following way. Well, so there's a misalignment here. So notice that this line is in fact a continuation of this comment, right? It's wrapped around, but it should have been all on one line. So this is part of a comment. So we want to try the following thing. We have three functions: main, first, and second, right? And main does the following: calls set jump, right, and save the state. Then it calls first. We go inside first, which calls second, and we go inside second. We print something here. Everywhere in each function we print something, and then we perform a long jump. And we're curious what happens when we perform the long jump, right? You'll notice that this printf doesn't print, right? You would expect that it would print because you're expecting that you're returning from second right here. Then we print. Then this guy is printed, right? This guy is printed, and then we come back here, right? And this guy is not printed. That's what we would expect. So what we're going to see is that this guy doesn't get printed, as a matter of fact, and this guy does get printed. So how does this happen? Well, set jump saves the stack for the current program, right, and the registers by the processor state. So that's what set jump is doing. So let's see how it works, right? So when we reach this point, set jump will save the state in this variable called bar. Then it calls first. We go inside first immediately calls second. We're here. When we perform long jump, the state is restored. So the processor is restored to the place, to the state it had inside here. And then it is allowed to continue execution. So when we execute long jump, the next thing that happens is that we will find ourselves at that very point, right? This point right here, right after the execution of set jump. So from long jump, we come back here, but this time set jump returns the value that we have here, right? So it's like a second return from set jump. We're forcing a second return of set jump, and we're controlling the return value. The return value is the one given here. The original return value was 0, right? When we call set jump for the first time, it will return 0, right? So because this is 0 and the negation here, we would go and execute first the first time, right? So I recap: first, then second, and then we execute a long jump. So the long jump simulates a comeback into this place of execution, right here, but a return value of 1. So now, because we have a return value of 1 and the negation, we're going to go here, we're going to print this, right? Notice that we have avoided the printing of this guy and finish. Okay, so this is a very interesting kind of execution. If you think in terms of assembly language, actually it's not that complicated because we're just returning the stack pointer to the value it used to have inside the first call to set jump. So then naturally, the state is restoring as if we're returning from set jump again, right? So when we execute the long jump, we're going back precisely after the we're restoring the state. We're sort of performing a hyperspace jump, right, and finding ourselves as if we're coming back from set jump, as if we're returning from set jump, but with a different return value. So this pair of calls, set jump and long jump, can be very easily used to implement exceptions in C. So this was the original designation. All right. So For the implementation of unchecked exceptions, let's take the code that we have just seen. On like 2 slides ago, we had a function f that inside a try block calls g, and then we're gonna later implement inside g is gonna call h, and we're gonna see the translation of that. So let's see the translation of that. So whenever we see a try block, right, the corresponding instruction is an if, and we're using inside the if a set jump. The set jump saves the state, and we're going to use this push and pop functions to sort of simulate the implement the operations on the stack, but it's going to work a bit different than the typical push and pop, right? The push is going to create a new element on the stack which is empty, doesn't put anything there, and returns the address, so that address of the new element on the stack can be passed as an argument to set jump, which can use the address to fill up with save state. Right, so push returns an address to a newly created, right, uninitialized element on the stack. Set jump uses that address to have a place to save the state. So that's why push doesn't really take an argument. And that's the translation. So try becomes an if, where we test set jump. Inside the if, the then body of the if, we can call as we did previously, right? So we're essentially copying over the try block, right? Becomes the body of the then block of the if statement. At the end of that body, because it means that if we reach the bottom part of the body, it means that we haven't thrown the exception. We don't need to throw the exception. Then we don't need to save the saved state anymore. We don't need the saved state anymore. And therefore we can pop that. And pop sort of simulates the destruction of the top element on the stack, but we don't return it because there's nothing to do with it, right? If we have not been in need of throwing an exception, we can just discard that, and we can continue execution. Now, the else branch of this if is going to be the correspondent of the catch clause, right? Remember, the throw will be implemented as a long jump. All right? So the long jump simulates a return from set jump, but with a different value, and that the different value will force a different path through the if statement, right? So we will go to the else. Inside the else now, we want to see what can we catch. So we're going to have a switch statement that dispatches on the type of the exception, and if the type of the exception is the E1, right, the exception E1, then we can handle the exception, right? So everything that was in the catch block will be there at case E1. After we have completed the case for handling exception E1, we need to, we have essentially handled the exception. So we're not in the process of handling any more exceptions. So we can reset the type of the global variable exception, which stores the exception currently being thrown, right? So that has completed. There's no point in keeping the exception in the global variable. So we reset it to no exception, and we go to finally, because remember, we still have to execute the finally. Now, where is the finally? Well, the finally is going to be the default of the switch, right? Imagine that we have an exception that is neither E1 nor E2, right? Where are we going to go? Well, we still have to execute the finally, irrespective of what exception was thrown. So we have to go to the default part, and the finally label there will um, uh, have all the code that resides in the finally clause of the try catch. Here we don't have one, right? So I have indicated this possibility that if we had a finally, all the code should go there. And at the end of the finally, what do we need to do? Is it the case, do we need to rethrow? Well, if we haven't finished the exception, the handling of the exception, it means that the exception still has a type that is different from non-exception. And in that case, we have to rethrow. And remember, every throw is done with long jump. So we're performing a long jump with the element, the saved state at the top of the stack, and a value of 1, so that we force going on the alternative of the if statement and not on the non-sequence. If everything has gone all right and we haven't thrown an exception, we will make it at the end of the function when we can return the value r. All right. So now let's see the translation of h. The translation still proceeds as usual. Right, the try block that we have here is translated into an if, and we're going to be throwing this E1. We are declaring these exceptions, right? And guess what? Whenever we see these exceptions in a object-oriented code, this will automatically invoke the constructor, so the exception will be initialized. Here we have to initialize by hand, right? So we have to fill up the type of the exception, we have to fill up the value. And then we can perform a long jump. This throw becomes the long jump that we have here. Okay? And similar here, right? So we have to set up the type and the value, and the throw is represented by a long jump. Now, in all these codes, this ... actually may represent if statements, so it's not necessarily the case that these two code fragments ever get executed, right? It may be the case that one of them gets executed, definitely not both, right? Because once we have performed one long jump, we're out of here. We don't have a way to go and execute the second one. But it may also be the case that none of them is executed because no exception is thrown. So then if we have made it to this point, we no longer need the save state at the bottom of the if state. So we can pop it, we can destroy it. Now the else branch is going to be the alternative. What happens if we have thrown an exception, right? What happens if one of these guys have been executed, right? The long jumps have been executed. We're going to come right here, right? We're going to return to the point right after set jump, but with a different return value, which will push us into the alternative of the if statement, into the else branch. And then here we perform a switch on the exception. And if this exception is one of those that we are supposed to handle here, well, we'll test for that, and all the code from here is going to go in here. Once we have finished handling the exception, we can indicate that we're done. And we can go to finally. Inside finally, we have to check, so inside finally, this code goes here, and we have to check whether the exception has been handled. And if it hasn't been finished completely, if it hasn't been handled completely, we have to rethrow the exception so that we give some other outer enclosing try a chance to handle its tries. Right, so this is the rethrow. If none of these has happened, right, so if we have made it peacefully to this point, then we just come out of if and we go and return the value r as usual. So notice the following very interesting thing. G does not change. That's a very powerful thing, right? So F has code related to exceptions. H has code related to exceptions. So both of them have to be translated following the systematic translation scheme, but G that did not change at all. G is unchanged. This is very powerful, right? It's a notation scheme that doesn't require a change in those functions that do not have to deal with exceptions. And as we go from F to G to H, when we do the set jump, we will return through, our return path will go through G without G having to know that, without G having to be aware about that. So therefore, G doesn't need to be changed. Okay? So only the source and the destination of the exception need to be changed. All the code in the middle doesn't need to be changed. It's important. All right. So it's a good place to take another break, and for the remaining part of the lecture, we're going to go into a small tutorial on C#, just to get an idea. So that will give you a chance to compare C# and Java.